Okay, so my name is Yu-Hsuan Lee. So I'm a professor and also the chairman of the Group A at the EE department. And my research field focuses on the video signal processing IC, as well as the compression and the image processing. So the primary features of this field is about how to translate your algorithm to the chip architecture. In this presentation, I'm going to have some selected research topics, including the following three core techniques. The first one is the image hazing chip with the little demonstration. The second one is the bandwidth compressor chip. The third one is the frame rate up conversion chip. So actually, in these three chips, we have designed from the algorithms to the chip architecture, and I'm gonna show those contents in following discussion. Then after that, I also give you the basic concept about the chip verification. At the last, I will give a brief summary. Okay, so here is the image dehazing engine. The primary motivation of this design is that in current vehicle market, we know that we always focus on the ADAS system. That's the advanced the driving assistance systems. So but sometimes we use the AI processing for the ADAS to make ADAS more automotive and smart. But if we have the bad weather, just like the hazy conditions right here, and we can find out this can dramatically drop the accuracy of the ADAS system. Okay, so now if we can put the image dehazing engine as the chip or as the integrated function inside the ADAS chip, then we can make these hazy images more clear. Then we can increase the reactivity for the ADAS to make them have much more accurate reaction to our vehicles. So that's the motivation of this design. And in this design, we don't use the AI processing because AI processing costs too much computation burdens. So we just use some sophisticated the image processing techniques, and these techniques can be divided into three parts: the airline estimation and the transmission estimation. The last part is the scene recovery. So you can find out this is designed from the algorithm to the chip architecture, and this architecture is the realistic chip. So you can see here around this chip we have the bonding wires, and we also have the three core circuit parts inside this chip. Besides, we also have the measurement result. We call this the Shamu plot. And we just put this chip onto our measurement device, the instrument, then we can sweep the frequency, and we also can adjust our working voltage right here. So you can find out, we want to find out the limitation of this chip. The green part means how this chip works, but the red part means its limitation. So we can easily find out its working area under different frequency and the VDD. And also this project has been published into the two IEEE papers. The first one is the IEEE CSVT. It's in the 2019. The second one is in the 2021. Okay, so before we deliver our design to the foundry, just like the TSMC, we always like to verify our system with the prototyping frameworks, just like this one. Here, we call this the FPGA. In Taiwan IC design industry, before we have the contract, we always download our design into this FPGA demo system. Then we can take this over to the customer to make a sample or demonstration to our customer. So we can find out this step is quite important. So after that, I'm gonna have some demonstration about how it works for our image dehazing chip. Let me switch to my clip. Okay, here we have a LCD monitor, LCD screen, and we put the hazy images onto the screen. Actually, that's a video. So we can find out in this video is to emulate the driving video with the hazy conditions. The next, on the top right part, we have the LPGA board, and we download our chip architecture into this LPGA board. Then we send our dehaze, the result to this LCD monitor, and we can see the primary difference between the hazy image and the dehaze contents. So I also design a button control. If we switch this button, that means we turn on the dehazing functionality so we can see the result on the LCD monitor. Okay, so here, when we turn on the switch, we can find out
Yes.
this image is much more clear than previous one, okay?
Amazing.
And it's real time. It's real time. Okay, that is the how fast this chip can be. Okay, so that's the primary function for this image dehazing. Of course, we need to make our dehazing speed much faster because our application is for the driving vehicle. Sometimes vehicle is in require higher speed, so we needed to make this reaction more quickly and to keep the safety reaction or safety decision from the ADAS more reliable. Okay, let me switch back to my slide. So that is why we always encourage our students before they deliver their chip to the TSMC, they needed to verify their system functionality or their chip functionality on the LPGA board. And we're gonna verify and the judge its performance on our platform right here. Okay, so here is the second research topic. That's the I/O bandwidth in the PS5 engine. So actually, PS5 is a famous gaming console from the Sony, and in 2020, its chip designer, the Mark Thiene, has announced a spatial design challenge. And in this challenge, it states that the I/O bandwidth of the PS5 is as high as the 5.5 gigabyte per second. Actually, that's a massive number. Why it can be that? Because in this gaming console, it focuses on the higher or advanced display resolution. That's the 8K at least 60 frames per second for the RGB content. So if you calculate its bandwidth with this spec, then we can find out it's about 5.9 gigabyte per second. So we can find out this one is a little bit higher than the limitation of the PS5 I/O bandwidth. But inside the PS5, it has a spatial engine. We call this the compressor. And this compressor can reduce the bandwidth requirement from the 5.5 gigabyte per second to the 8 or 9 gigabyte per second. Here we can find out with this compressor, it can increase the bandwidth capacity from the 5.5 up to the 8 or 9 gigabyte per second. So this is the key point. If you want to have the pure high-speed circuit to transmit such a higher bandwidth, it's almost impossible actually. But if you can use the compressor, just like the image or video compressor, you can boost its bandwidth capacity. So here is our second research topic. You can find out here, we have developed the algorithm down to the chip architecture. Then here is some architecture, especially for the digital circuit. We can find out inside the chip, we have 4 stages, including the buffer, including bitstream packer, including the one-shot comparator. And with this functionality, we published this work in the IEEE transaction on VLSI system. Okay, so that's the second the research topic. And here is the third research topic. We call this the FIUC engine, that's the frame rate up conversion. Owing to the physical limitation from the LCD TV, we know that we have some motion blurs for the LCD, the LCD moving content. And this problem can be efficiently solved by the FIUC. That indicates you just need to increase your frame rate, maybe from the 60 Hertz to the 120, then we can reduce this drawback. And here is our research achievement. Inside this research, we use 3 techniques. The first one is the BD3DRS. We use that to provide the initial motion vector. Then after that, we further use the STMVR to refine our motion vector. Then after that, we use this result to create the complete the video content for our final destination. Then all these stages have been realized into the chip. We also can find out here, we put the SRAM around the corner. With this frame plan, we can reduce the IO drop efficiently. And here is the IO bonding wire. Okay, so that's the stage 1, and here is the stage 2. Okay, so let's talk about the chip verification. All above 3 research topics are processed by these verification steps. And the first one, maybe we use the C model or any other high-level language to create your algorithm. And actually, this model has 2 primary purposes. The first one is to demonstrate your performance and make a comparison with the other works. The next target is to make the verification with the results from our hardware. For this hardware, we usually use the Verilog core to get its results. So on left-hand side, we have the C model or a high-level language model. On right-hand side, we have Verilog. So we can compare each other's result together. Then we can make sure whether our result is correct or not. Okay. So after that, we can easily put our design to the TSMC. Here, I have the special announcement to all India students. In Taiwan, we have very precious resource to train our students for the IC design. We have a special institute. We call this the TSRI, the Taiwan Semiconductor Research Institute. With this institute, it can provide any chip design resource, including our design, including our above 3 research topics, and we can deliver our chip architecture to the TSMC, and we have its fabrication. So that indicates students pay for nothing to realize their chip, just the knowledge to the chip architecture, and TSMC can fabricate your idea into the chip. That is the space. That is the precious resource to train the chip design students in Taiwan. That's for free for education. Okay, so here is the brief summary. My lab is multimedia circuit and system lab. As mentioned earlier, I focus on the algorithm designed to the chip architecture on the image and video signal processing. And from the TSRI, and we can let our student design the layer chip and realize layer chip by the TSMC 0.18 micrometer, maybe even advanced ones, okay, depending on your applications, for free. Okay, of course, that's for education, even for the India students, okay. And students can also enjoy their journey from the ICT side to the IC measurement. In the TSI, we also provide the high-end measurement institutes, so we can utilize this institute to verify our chip performance. Okay, so that's the pressures, the design resources for our students. Okay, many thanks for your participation. Thank you.